very useful to express the acceleration along these terms. And you'll see it later on. Those of you who will learn when you go and take the course in dynamics, later on in part of your pre-professional courses, those of you who move on to mechanical and I think both electrical engineering, mechanical and civil engineering, you'll have to learn dynamics. You'll run into this again. But here's where we start with. We're gonna express. Let me see what my note telling me here. Yeah, let's start with this. We're gonna let V. Suppose V, and this is a scalar function. In other words, this V is a real valued function in time. So let it be the speed, and the speed of the particle, or if you remember, the speed is the magnitude of the vector V. Okay? And of a particle moving along a space curve. All right, so then we're gonna go and all of a sudden divert to the unit tangent vector as a function of time. And do you remember the definition of the unit tangent vector? R prime over its magnitude. Okay, and remember, R prime is also a function of time. And now, what is R prime? Well, R prime is the velocity, isn't it? And so what do we have here is the magnitude of the velocity. Okay, we just define the magnitude of the velocity as V, right there, right? And this is V of t. Remember, this is V is a function by itself, so we might as well write it like so. Notice that the difference. This is V without a vector notation, so it's the magnitude. All right, so what do you get from that? If I want to replace V, write it in terms of the tangent, then what follow from this statement that the vector V equals the scalar component, which is the magnitude, and the direction. And this is more than just semantic. Because if you look at it very carefully and interpret it, what is the interpretation? It tells that the velocity is a vector, has two components. Remember, it's a vector, so it has a magnitude, and then always the size of each one is 1 unit. So magnitude times direction, or the magnitude and direction. And we'll use that later on as we continue to develop this expression. So now we're going to take the derivative of both sides because we're interested in acceleration. So we differentiate both sides to get the following. The derivative of V is, of course, A. And we have a product here, so we need to apply the product rule, right? So it will be V prime of t times the vector t plus V times the derivative of the vector, like so. Okay? This V is always a scalar. That's the speed, remember? Because it's still a function of time. It's a scalar, but it's a what's called real value function. It's a traditional function. That's why I put the t in there, because I realize that we are so engulfed in vectors, and we think that if you don't see the vector sign, then it's a constant. So it's still a time function. Okay. So do we call this equation star? Because we'll go back to it. I'm sorry, there was a question or comment? No? I thought I heard somebody asking. All right, now we bring the curvature. So recall the curvature, K. Remember, the curvature is also, it's not a constant, it's a function in time. Okay, what was the definition of the curvature? Remind me. Magnitude of t prime over magnitude of r prime. Okay, good. So now let's see what we can do with it. What is the magnitude of r prime, the denominator? It's v of t, right? Not the vector, it's the speed. Okay. All right, so now we can find an expression for t prime, because I need t prime somehow. So at least at this point I can extract an expression for the magnitude of t prime. And the magnitude of t prime, which is a scalar quantity, it will be k of t times v of t. Okay? And we call this equation double prime. And we move on in developing this expression, the following expression. So, at this point, let me tell you what's my motivation. My motivation is to take the equation that I denoted with prime and replace different component, like the t, mostly right now I'm struggling to find an alternative to t prime, to the vector t prime. So let's see what I'm doing next. Next, I'm going to recall another vector, and I'll recall the unit normal vector. N of t. Okay? So again, remind me, what's the definition of the unit normal vector? T prime over the magnitude of t prime. So, and remember what I was after? I was after t prime. So I have t prime, and let's write it as t prime of t, and now we have the magnitude of t prime times the vector n. Okay, now we replace, we plug in the double prime, because we have an expression for t, the magnitude of t, so use the expression double prime to replace the magnitude of t prime. So that will be replaced by kv, remember? So we have now the vector t of t. Instead of the magnitude of t prime, we have k of t times v of t times the normal vector of t, like so, right? All right, now go back to equation star, okay? And now use or replace, now I need to replace t prime, the vector t prime, in equation star, and have equation star read, if you recall, the acceleration equals v prime t plus, we had v prime times the vector t prime, so now we have v It's all function of t. So now we replace that with this, and we have k of t, v squared of t, n. And that's it. And so we have a tangential component and a normal component. Okay? Equation star. Yeah, we replaced, here's the equation prime. V prime t plus v t prime, and what we did, we replaced, oh, this one. Yeah, thank you. Yeah, we replaced it with v prime. Right here. So, or now we can write a of t equals a scalar component that is in the tangential component, like so. Remember, this is not a constant, it's a function of t, plus a normal component of the acceleration in the normal direction. Okay? And this is what they jump into physics, and I want to, this is a remarkable result, and I'll tell you in a second why. Okay, where a of t equals v prime, and the normal component equals what? Equals k v squared. Now, what's so remarkable about k v squared? Okay, recall that k equals 1 over r, where r is the radius of curvature. Therefore, the normal component is v squared divided by r. And you can say, and centripetal forces or radial force or radial force, now I'm moving to physics, is given by Newton's second law. F equals ma, as F in the normal direction equals m v squared over r. I'm sure you've seen this, and I think last time when did I show you? I took my belt and show you. So let's at time it's beneficial to express both components in terms of just the position. So we can express the two components, a sub n and a sub t, the normal and centripetal or the radial component of the acceleration, in terms of r prime and r double prime. Okay, so let's look at a sub t. A sub t is the derivative of the speed. Okay, but the speed if you work the remember the velocity, the speed is v divided by its magnitude. Right? If you do the quotient rule, you end up coming with the following expression. If you apply the quotient rule, you'll end up seeing it will be the velocity vectors dot the acceleration vector divided by the velocity. Initially it's the velocity squared, but it's being reduced. And then, let me double check on something here in my notes. This is something that I hope I did not skip. No, I did not. It's true. So now we can write it. This will be the first derivative of r, so we can write it as r prime, and this will be dot r double prime, and this will be the magnitude of r prime. So this is the expression for the tangent acceleration. The normal acceleration require a little bit more work, and it will be, if you look at the component, it's kv squared. Well, k, if you remember, is the cross product. It's r prime cross r double prime, and we take the magnitude, and then we divide it by, remember by what? To the cube. And then we have v squared, but v squared is the magnitude, is the speed squared. The speed squared is the magnitude of r prime. So we square it, and at the end, what we are left with is r prime cross r double prime. We have a magnitude here divided by the magnitude of r prime. And these are sometimes these components are a little bit more convenient to work with. Okay, and I have an example for you on the next page. Very short example, I think. And then we'll get Nate here to talk about the next section. You need a what? I thought you said I need to pee or something. And I was wondering why you come so close to me. Well, I have this yellow stuff here, but don't mix it with it. It's funny, I don't care how you look at it. Oh well. So, you're full of demands, this all right, so we have this vector, fairly simple vector, and we need to find the component of the acceleration. So let's look at first at the first derivative in terms of t, and it will be 2ti plus 2tj plus 3t squared k. The second derivative will be 2i plus 2j plus 60k, right? I think that's what we need to do both. So let's look first at a sub t, and that would be r prime dot r double prime divided by the magnitude of r prime. So let's do the dot product of these two. Okay, so 2t times 2t, 2t times 2 is 4t, plus 2t times 2, 4t, so we have 8t total, and plus 3t squared times 6t, or 18t cubed. Okay, and we need the magnitude of r prime. So for the square root of 4t squared plus 4t squared, 80 squared, plus 9t to the fourth. So we'll write it as square root of 80 squared plus 9t to the fourth. But here we need to do some simplification. We can factor out t, so we have we can factor out also 2, but we'll keep that 8 plus 18 t squared divided by 8 plus 9t squared, square root of 8 plus 9t squared. After factoring 2 from numerator and denominator. Let's this one 9t I factor t, so the t cubed becomes t squared. For the normal component, we need the cross product. It's not hard stuff. The normal component. Let's look at the cross product. So ijk r prime 2t 2t 3t squared, and r double prime 2 2 and 6t. Okay, let's check out the I component. 12t squared minus 6t squared, so we have 6t squared I. Let's check out the j component. Instead of putting negative, I'll go in reverse order. 6t squared minus 12t squared, so we'll get negative 6t squared j. What about the k component? Are we supposed to have a k component? There is no binomial component. Turn out there is no binomial. You can see it's 4t minus 4t, it's 0. There is absolutely no binomial component. So a sub n, a sub n is now the magnitude of the cross product. So the magnitude of 6t squared I minus 6t squared j divided by the magnitude of r prime, which is 8t squared plus 9t to the fourth inside the square root. Once again, the magnitude here, we can factor 6t squared, right? So this would be 6t squared, and that's a common factor, and we have the square root of 1 plus 1. So the square root of 2 divided by, and factor out the t, so you have t square root of 8 plus 9t squared, and eventually you come up to the solution, which is 6t square root of 2. Actually, we put the coefficient ahead of the variable, so we write 6 square root of 2 t divided by the square root of 8 plus 9t squared. the magnitude, you factor 60 squared and you have I minus j. Okay? And what is the magnitude of I minus j? Is the square root of 1 squared plus negative 1 squared. That would be square root of 2. Okay, I think, Nate, this is a good time for me to stop. There may